Now, truck versus bullet example. Look at the top half of the screen. We have two extreme scenario that can both be deadly because of high momentum. First, look at the small bullet. Its mass is tiny, only 200 grams, but it travels at an incredible velocity of 1000 meter per second. Because the velocity is so high, the product m into v gives it a massive momentum, which is why a small bullet can kill a person. Now look at the heavy truck. It is moving at a very small speed of just 5 meter per second, which is like very slow bicycle, but its mass is huge, 10,000 kg. Because this mass is so massive, the product m into v again result in a very high momentum. This explains why even a slow moving truck can be fatal. Now let's look at the bottom half of the screen to understand why momentum is a vector quantity. Vector means direction matters. In physics, we usually take the right side as positive and the left side as negative. Look at the first ball on the left. It has a mass of 1 kg moving right at 10 meter per second. Its momentum is P is equal to 1 into 10 equal to 10 kg meter per second. Now look at the second ball on the right. It also has a mass of 1 kg, but it is moving to the left at 5 meter per second. Because it moves left, its velocity is taken as negative. Its momentum becomes 1 into minus 5 is equal to minus 5 kg meter per second. The minus sign here does not mean the value is less than 0. It simply tells us that the momentum is directed toward the left. Now, Now we are going to start one of the most core concepts in all of mechanics, Newton's second law of motion. In our previous slides, we studied that inertia make an object resist, change, and momentum tell us how much motion a moving body contain. But how do we actually calculate the amount of force needed to change that motion? Newton's second law gives us the exact mathematical connection between force and momentum. Let's look at the statement on the screen. Look at the top statement carefully. The rate of change of momentum of an object is directly proportional to the unbalanced force applied, and the change in momentum is in the direction of force. Let's break this down into simple physics terms. If you want to change an object's momentum quickly, meaning you want to speed it up or stop it fast, you need to apply a large unbalanced force. Mathematically, we write this relation as F is proportional rate of change in momentum. And remember, whichever direction you push or pull the object, its momentum will change in that exact same direction. Now, let's convert this proportionality statement into a proper equation that we can use to solve numerical. Look at the step on the left side of your screen. Rate of change in physics always means dividing by time. So we can rewrite our relation as force proportional change in momentum upon time. To remove the proportionality sign and bring in an equal to sign, we must introduce a constant which we call k. The equation becomes F is equal to k multiply change in momentum divided by time. Experimentally, the value of this constant k is found to be exactly 1. When we put k is equal to 1, we get a final beautiful law on the right side of the slide. F is equal to change in momentum upon time. Now, understanding the initial and final states. Look at the top of screen. Imagine an object of mass m moving along a straight line with an initial velocity u. Now we apply a constant unbalanced force F on it for a time duration t. Due to this force, its velocity changes from u to final velocity v. Let's calculate the momentum for both states. First, our initial momentum before the force is applied will be mass times initial velocity, which is m into u. Our final momentum after time t will be mass time final velocity, which is m into v. Now let's look at the mathematical step on the left side. What is the total change in momentum? In physics, change is always calculated as final minus initial. So, the change in momentum equal mv minus mu. According to Newton's second law, force equals the change in momentum divided by time. Let's substitute our value into that formula. F is equal to mv minus mu upon t. This is the foundational mathematical expression of second law. Let's move over the right slide on the screen to complete our derivation. If we take the mass m common from the numerator, our equation look like this. F is equal to m v minus u upon t. Now, think back to our first chapter, motion. What is the formula for acceleration? Acceleration A is the rate of change of velocity, which is exactly v minus u upon t. Look closely at our force equation. We have v minus u upon t, which the letter a. Our equation simplifies beautifully into F is equal to m into a. This proves that force is simple the product of mass and acceleration. Now we have a problem. Look at the top section of the slide. Let's read the question together. Calculate the magnitude of the force required to increase the speed. Let's look at the diagram to extract our data. We have a box with a mass m is equal to 5 kg. Its initial speed u is equal to 3 meter per second. A force F pushed it for a time duration t is equal to 2 seconds. After 2 seconds, its final velocity becomes v is equal to 7 meter per second. Our goal is to find the exact value of this force F. Let's look at box number 1 on the left side. Before we can use our force formula, we need to know how much the box is accelerating. We know the formula of acceleration from our equation of motion is a is equal to v minus u upon t. Let's substitute our known value into the equation. A is equal to 7 minus 3 divided by 2. A is equal to 4 upon 2. It means 2 meter per second square. So the box is accelerating at a rate of 2 meter per second square. Now, applying Newton's second law and final answer. Now, move over to the middle section box number 2. Now that we have the acceleration, we can easily calculate the force using Newton's second law. F is equal to m into a. Let's substitute our value for mass and acceleration. F is equal to 5 into 2 is equal to 10 Newton. Look at the box number 3 on the right side for the final presentation. The magnitude of the force required is 10 Newton. Never forget to write the correct unit, which is Newton or kg. Dot meter per second. Key takeaway and summary. Let's play with one another question. Let's read problem statement at the top together. A car of mass 1000 kg is moving with a speed of 72 km per hour. and it takes 4 seconds to stop after the brakes are applied. Calculate the force exerted by the brakes. Let's break down our given data. Mass of the car is equal to 1000 kg. Initial speed u is equal to 72 km per hour. Time taken to stop t is equal to 4 seconds. Since the car finally stopped at the red sign, its final speed v is equal to 0 meter per second. Our main challenge here is that the initial speed is in kilometer per hour, but time is in second. We must fix this first. Now look at box number 1 on the far left. To convert speed from kilometer per hour to the standard SI unit of meter per second, we multiply the value by the fraction 5 by 18. Let's calculate it. U is equal to 72 into 5 by 18. Since 18 for the 72, our equation simplify to 4 into 5, which gives us an initial speed of 20 meter per second. Now all our units match perfectly. Now move to the box number 2. In the middle, let's find the acceleration using our standard formula. A is equal to v minus u upon t. Substituting our updated value onto the formula, a is equal to 0 minus 20 upon 4. A is equal to minus 20 upon 4 is equal to minus 5 meter per second square. Notice the negative sign. This negative value indicates the opposite direction, which makes perfect sense because the car is slowed down to a stop. Let's look at box number 3 on the right side to find the final force using Newton's second law. Let's plug in our mass and our negative acceleration value. F is equal to 1000 multiply minus 5 is equal to minus 5000 Newton. Our final answer is that the force exerted by the brakes is minus 5000 newtons. Be sure to explain this clearly in your exam. The negative sign simply shows that the brakes force act in the direction opposite to the motion of the car to bring it to rest.